Alright, Chapter 3, Capacitor Inductors Complex Impedance. This chapter introduces the concept of complex resistance or impedance by solving the two reactive circuits element of the capacitor and inductors. We will study the capacitor and the inductor using a different equation for analysis. From these derive the impedance of the capacitor and inductors used primarily for the circuits from time-dependent voltage such as the AC circuits. AC voltage. Most electronic circuits involve a time-dependent voltage current with the input with the class of time with the dependent with the subsidal voltage or concurrent, known as AC or alternating current. Kirchhoff's law of the Ohm's law is still applied, but there is always applied with the one most careful the difference between the time and average of the impedance quantity for the AC voltage or signal is form as voltage is equal to voltage T. Voltage time is equal to voltage period. Peak voltage time is equal to voltage peak voltage at cosine of angular frequency time, where W is equal to the angular frequency, Vp is the amplitude of the waveform, and or peak voltage, and T is equal to time. The angular frequency related to the frequency is F by angular frequency equal to 2 times pi frequency of a period of time is related to the frequency of the period of time. Frequency of time is equal to 1 over the frequency of the useful voltage, also commonly defined include with the peak-to-peak voltage, which is twice for the amplitude of the root mean squared voltage with voltage root mean squared. The voltage amplitude peak-to-peak form voltage is greater than is divided by the square root of 2 average power over the resistor of the AC with the dp over the root mean squared quantities. Power is equal to amperes root mean squared times voltage root mean squared, or equal to 1 peak voltage peak amp divided by 2. But the important enough of the voltmeter for the ammeter of the AC mode that actually return the root mean squared value of the current voltage, which most of the real-world signals are non-signal. AC signals are still used extensively to characterize circuits throughout the techniques of Fourier analysis. Fourier analysis are convenient way with the characterized rate of change with a function, right, with a true function with a linear combination. Set up the functions have particular ease with the characteristics to deal with it analytically. In this case, we consider the trigonometric functions. It turns out we can write with the function with an integral form. Voltage time is equal to the logarithm of frequency of the voltage frequency cosine of the angular frequency times the other frequency of the distance times the angular frequency. The process called Fourier analysis means the function can be written with an integral or simple sinusoidal function. In this case, the periodic waveform an integral becomes the sum overall of the harmonic for the period with an integral multiplicative frequency over the period. Voltage time is equal to the logarithm of the n to the n, with the base of n to the an. Cosine amps to the n to the base of the n cosine times n times the angular frequency times time of the frequency. With the implication mathematical fact to figure out what happens with the integral voltage of the linear circuit that will know everything about the operation, even every arbitrary input voltages. Complex notation, we replace the sinusoidal function exponential to the calculus bookkeeping easier still, but include both phase and magnitude information with it defined as E over, or where E is equal to E amps over the frequency is equal to cosine frequency plus amp sin frequency, or amp squared is equal to -1. General procedure with the notation chain with the problem of complex algebra to replace the cosine of the angular frequency time times the amp times the volt amp frequency time. Solve the problem, take the real part of the solution, and the answer it did. 2 capacitors. One of the most basic rules of electronics and circuits must complete with the current to flow of the week. This week we introduced an exemption to that rule. The capacitor usually a small break in the circuit with measuring with the resistance of the capacitor will find with the open circuit how an inside end of the capacitor to leave with a little place for the charge reserves. Reservoirs which can store charge for some short time, and we do not nerve the break of the negatively charged initial flow of the one side to and out from the other side with the 2 leads with the connected for the fact of the signal of the capacitor looks like a short circuit, but after a while the capacitor reserves the available and current stuff with the nodes with the break in circuit of the slow signal Slow signals capacitors looks like an open circle to win first one with the show, but it depends on the capacitor of the result with the circle. This week you learn how to determine the fast and slow of your cell with the capacitor. Three major roles: electronic circuits, although the threes are just variations of one basic change: integrators, high and low frequency filters, and DC isolators. In order to perform a functional analytical, we'll need to introduce the number of the new concept of some of the significant mathematical formalizations. Formalisms in this process. We also develop a number of the new concepts in analyzing electrical circuit. The capacity of the device for the storage charged electrical energy consists of the two parallel conducting planes. Some non-conducting material between the planes is shown in Figure 3.1. On the right, the voltage applied with the positive charge collects one plate, with a negative charge collects the other plane. Since they are attracted to each other, they're in a stable state. If the voltage is changed again, the capacitor charge capacity with capacity is Quantity is equal to capacity times the voltage of the relay with the curve of the and the capacitor of the cube with the voltage across the leads is volt V. Capacity is measured in farads. A farad is very larger than most units of the millifarad or N-farad or P-farad, picofarad. Sometimes the device's most electronics and components have been small parasitic capacity due to the lead of the design. Capacitors also store the energy electrical field generated with the charges on the two plates. The potential energy stored with the capacitor with the voltage is on. So the voltage is equal to 1 times the 1 over 2 times the capacitor times the voltage amp. Usually energy is equal to 1/2 over the capacitance. Capacity times the voltage squared. Usually speaking, the terms of the current, but they analyze the circuit, noting that the current is the rate of change of the charge. With the rewriting the definition of capacity with the terms of the current says voltage is equal to 1 times the capacity times the capacity, the stored capacity equal to 1 times the capacity with the to the rhythm of I amp distance and time. Amp times capacity equal to the distance of the voltage over the distance of time times the current capacitor times the voltage. This will change the integrated function of IT and the monitoring of the voltage as the current change of the capacitor. Differential function of voltage T, which by putting it across the capacitor, monitoring the current flow with the voltage changes. Or a simple RC circuit, we'll start looking into the detail of the simplest capacitive circuit, which shown in Figure 3.2 with the right with the RC circuit frame. Simply putting the resistor and the capacitor together with the voltage divider. We'll put the resistor first, the potential for the capacitor with the ground. Applying Kirchhoff's law of the circuit, we can see that the same current flows with both the resistor capacitor, and 2 the sum of the voltage drop of the two elements will equal to the input voltage. This can be in the form of the following equation: voltage input and input time of the resistance plus 1 over the capacitor to the apply. Written in an IDT. We can also show the written as voltage input resistor over the times 1 times over the 1 amps times the 1 over the resistance capacity with the DT differential IDT. We also give the form of the differential equation following with the distance voltage input over the distance and time equal the resistance over the distance and amp over the distance and time plus amp over capacitor. Capacitor voltage input equals resistor, capacitor, inductor, and plus an amp. These equations show the time and the measure for the units for the IRC with the will see with the dependent quickly the time change during the RC time interval. Current changes quickly, the most voltage will show up at the graph of the resistor, the voltage graph of the capacitor show for the charge for the integrator with the current with the voltage changes slowly. The most voltage shows up at the graph of the capacitor and charge for the usually recover the small current with the voltage graph of the resistor stays small. But what happens immediately intermediate time to determine equivalently we will have to develop some of the sophisticated mathematical equation techniques. Solution of the RC circuit rather than produce the general solution with the concentrate with the two special cases particularly useful with the first with the constant voltage and the second will be with the syncytial input. To study with the constant supply of voltage on an RC circuit with the left side of the equation R12 with the equal with the constant voltage with the have the simply homogeneous differential equation simple solution with the current the decaying potential with the amp that equal the amps output with the E the decay exponentially will account with the initial indication that after a few times of the RC time period, the solution will decay away from the supply voltage. And let's not consider the other solution prior selection. In the prior section, we argue that we can understand the RC circuit behavior with the syncytial input. We can deal with any of the arbitrary input, but there is important one. Let's look at the simple RC circuit supposed to be applied with the drive as a simple sine wave with the input with the voltage input with the voltage output with the equal to the cosine of the frequency with time. Plus the the notation mean with the set of the drive voltage, voltage input with the voltage output conventional, and the amp frequency time. We just have to remember the real part of the end of the calculation. If the drive of the voltage drive of the differential equation, then it becomes a relatively simple inhomogeneous differential equation, where capacity of the distance of the voltage input over the distance time will equal the capacitator of the voltage output over the amp frequency exponential into the amp the frequency time equal the R resistance capacity over D times amperes over dt plus amperes. The relatively simple because over the often physics at night is well with a memorized solution. Less ways to get to the solution. Note that it mathematically looks like with a different harmonic oscillator. We give it the same solution standard recipe the first order of the linear differential equation, rewriting the equations, then multiplying the expectation by the root. Left-hand side equivalently written in order with the total derivative of the multiplication rule. So we now have this equation as integrable can be written as the integral straightforward yields of the following expression. In the first term, the U of the state state of the oscillator behavior, the driven current circuit with the second term of the describe of the transient behavior, the current switching on to the deriving voltage, only interest in the long-term behavior of the circuit, and neglect the second term and the concentrate on the first, for a little bit of the bit of algebra, we rewrite the steady statement current. The second fraction is interpreted with the phase term of the tangent of 1 of the frequency of the resistor and capacity, so the expression current becomes, and then with the real solution of a simple RC circuit can be obtained by taking the real part of the equation 23, left it with the exercise to read. Solution, a simply RC circuit supplied with rather complicated and involved, however, simplified with considerable when we plug the equation 23 back into the equation. Original integral equation, Kirchhoff-Loop's law, with the equation 10. After integrating the potential little bit of the algebra, we obtain voltage input time of the frequency is equal to amp times the resistance plus the amp times 1 divided by amp frequency capacitor. The remarkable simple expression looks like the like of a Kirchhoff-Loop's law with the relation of the resistor. Example, the capacitor terms behave with a frequently dependent imaginary resistance. RC impedance will obtain the same solution as the one obtained with the original voltage divider, as long as it is assigned imaginary frequency dependent with the resistance to the capacity of the imaginary part. It just means that it will produce a pi over two-phase shift between the voltage. Currently, this initial input will be called the impedance capacitor equal to 1 over the amps of the frequency of the capacitor. Now the solution of the RC divider becomes some simpler. We compute the total following current through the circuits, the voltage across the element of the current time element, and produces the voltage drop of the resistor, largely the same as before. For the capacitor, where the following voltage drops. Everything calculated in the sum of the voltage drops across the two elements should be equal to the input. Remember that your actual waveforms take the real part of the complex solution, and then complicated the limits for the high frequency, low frequency. Even to remember, high frequency is results in zero. The capacitor is like short of voltage that shows across the resistor. Low frequency is frequency that results in pi over 2 of the capacitor. Is likely an open circuit. The voltage show the cross. Across the capacitor, with the leading terms of the elements of the small voltage, you find that the high frequency of the voltage across the capacitor is integral to input voltage, while the low frequency of the voltage across the resistor are additive to the input voltage. This says that as long as the important frequency high of the capacitor integrate with the input voltage, input frequency small with the resistor is different voltage with the intermediate frequencies, mixture of the sum of the high, some of the low frequency result, but may not be simple to determine from the voltage divider or the algebra, even the complex notation, efficiently noting voltage capacitor as negative pi over 2 with the out of phase of the voltage resistor. In 3, inductors. An inductor is a coil wire solenoid which can be used to store energy magnetic field that generates, and is mathematically similar to the capacitor exactly that the opposite behavior of the behavior of the short circuit with a low frequency as an open circuit with a high frequency. It passes the low frequency signal with the blocks high frequency signals. Energy stored in field, the inductor will, with the inductance L will given in the following formula. The energy is equal to 1/2 the voltage, the inductance times the ampere squared. This is SI indicated by the Henry system of instruments induced inductance is a Henry commercial available inductors of inductance for the range from nanohertz, nanohenries, millihenries, small millimeter size, centimeter size solenoids. Typical inductance range for the Henry's magnified coil with inductance of millihenry range, sometimes changed have the inductances up to several henries. Most electronic components have small with the parasitic inductions due to the leads in the design. For example, the wire wound power resistor. Figure 3.3 show that the inductor consists of coiled wire with a solenoid and the dash arrow B for the reference of the magnetic field generated with the current and the conductor. The electrical circuit of voltage, electromotive potential for the generator across the terminals, inductor for the current change with the Farad laws of the voltage drop of the following circuit. The voltage equal to the inductors of the distance, the amperes of the distance of the time. The equation C with the indicator of the operator is exactly opposite of the capacitor and indicator difference for the current and integrated voltage. The inductor is a resistor circuit with a value of the inductor resistor circuit, some way with the derived with the operation of the resistor capacitor circuit. We start with the Kirchhoff loop law with the inductor resistance capacitor circuit is figure 3.4 below. We find that if voltage input over the amp of the resistor plus the inductors over the time of the distance for the amp over the distance and time, they apply with a constant voltage solution calculated with the technique we developed with the resistor circuit. We calculate the amp time is equal to amp output of 1 times the exponential over the negative resistance over inductance times time. The circuit approach with the current amp output is equal to voltage input time over the resistance with the time constant with the inductance is equal to over the resistance. Inductance impedancy instead of solving the differential equation of the inductance resistance circuit for the sinusoidal apply with the input voltage given in calculation 1415 with the resistor capacitor circuit. We'll just assume that the current formula in amp at time is equal to amp output exemption over the amp frequency time over the frequency. We plug the Ansata solution between the different equation 31 and that from which to deduce the inductor become the resistor frequency, the dependent imaginary resistant independent inductors. Therefore, independent inductors equal to amp times frequency times the inductance. Just as the RC circuit applied with the Ohm law circuit to calculate with the total current of the resistor and inductor in series we obtain, where the phase is given in the tangent of the frequency of the over inductancy resistance. Because relate the voltage dropping off the resistor expression with the current that voltage resistance equal to amps times time with the resistance equals voltage output with the cosine of the frequency of the amps to the amp and frequency time times the frequency divided minus frequency power. Voltage drop of the inductor calculated in the same way. If everything correctly calculated, the sum of the voltage drop off of the two elements equal to the input voltage. You give it the waveform with taking the real part for the complex solution with a this is a little complicated. For the high frequency, low frequency are even. Remember, the high frequency with the frequency with the equal to is resolved in a pi over 2. The inductor like open circuits, all of the voltage show with the curve of the inductor. Low frequency, the frequency is equal to 0. The input of the short circuit with just a plane where the voltage shows with the curve of the resistor. Who should be the point of the voltage inductor is always positive pi over 2 for the out over the phase of the voltage of the on a resistor. For transformers, transform with an ingenious combination 2 inductor that can be used with the transfer power between the two circuits with the magnetic coupling transform change with the input voltage without affecting a single shape of the similar voltage divider over the last week. However, the important difference increase of the week will decrease the signal amplitude AC voltage because the time varying AC input work much harder to fabricate. Usually does not work well with very fast signals and inductors since inductors block high frequency transformers are commonly used major component of the DC power supply since they convert 120 volt AC with the wall with the voltage with a smaller voltage closer to the desired DC voltage of 5 volts to plus or minus 15 volts. Schematic symbols from the transformer are shown in figure 3.5. Above, the transformers are passive devices simultaneously change the voltage of the current with a circuit that have at least 4 terminals. 2 inputs called primary and 2 outputs called secondary. There's no real difference between the input output of the transformer. You can simply flip it around. You have the secondary input and the primary output as the output. However, for the sake of clarity, we will assume that the use of the primary input and secondary for the output. The coupling between the input and output is done magnetically. This allows the transformer to number the interest benefit included. There is no DC connection between the input and output. The total of the transformers often used to isolate one circuit from another. The transformers only work with a varying signal when the inductive coupling between the coils is greater than the resistive loss. Since there is no external power over the output power, there cannot be greater than an input power. The power is equal to voltage power over the amp power greater than or equal to the voltage S over the amperes. S, usually assuming the A quality of small resistance heavy than the resistance law with the coil of power, lead cheaply designed transformer to note with the input with the output significantly strong coupled to each other depending on the device. Signal output port will be less than the input power. The transformer the most commonly used the change of the line voltage for the 120 volt root mean squared at 60 hertz into more convenient voltage for the high power transmission uses transformer to increase the voltage, decrease the current with an induce the amperage of the resistance power loss in the transmission wire for the R circuit will use the transformer to reduce the voltage and increase the current. Transformers are characterized with the ratio of the number of turns of the input of the output winding for the magnetic coupling. Ideal transformers will ensure the number of the turns over the current flowing and the same with the input output, and then since the voltage will not change with the opposite of the number of the keep of the input and output power ratio voltage same with the ratio terms voltage voltage source over the voltage power over the Newton source over the Newton's power of the transformer. They usually can transformer. They usually step up or step down according to whether the output voltage increase the degree of the transfer, the impediment, the circuit, the change of the ratio of the voltage in over the amps, using our rule of the ratio output impedance input impedance wherever the ratio turns. So if you use the transfer, step up transfer, increase the voltage of the impedance of the output relative to the input with the transfer, and step down with the transfer to decrease the voltage impedance as is output. Design exercises, and then lab. And we're not actually taking this class, but we have got it off of a website. Week 4. All right, week 4.